This is the final lecture in calculating equilibrium concentrations from Kc. We will work one last example in this lecture. As we have seen in the previous 3 lectures, we have learned how to calculate equilibrium concentrations from initial concentrations and the value of Kc for an equilibrium reaction. In this lecture, we will practice on one additional example problem. Additionally, we will once again see how to incorporate the reaction quotient Qc into this type of problem. As before, please be sure to pause these lectures regularly so that you can work the problem along with me. This is still the best method for developing the skills for solving this type of problem. We will once again restate the procedure. Once we're done, please pause this slide and write down each of these steps so that you can have them at your side as we work this problem. Step 1. Once we have read the problem, we will fill in as much of the ice table as we can. If a pure solid or liquid appears in the reaction, we do not need to tabulate its values. 2. If either the reactants or products have an initial concentration of 0, then the reaction will proceed in the direction to form these species. Otherwise, we must use the value of Qc to determine the direction of reaction. 3. At this point, we have to introduce a variable in place of how much each concentration changes. 4th, we then determine what the equilibrium concentrations should be in terms of the initial concentrations and the variables. Lastly, we substitute the algebraic terms into the equilibrium constant expression and solve. Here is our example. Consider the equilibrium reaction of N2O4 gas decomposing to 2NO2 gas. At 373 Kelvin, the Kc value for this reaction is 0.211. Initially, you have a container with 0.750 molar N2O4 and 0.525 molar NO2. Calculate the concentration of all species once this system reaches equilibrium. The first step, as always, is to write the Kc expression. In this case, we have the concentration of NO2 squared in the numerator and the concentration of N2O4 in the denominator. Now to build the ice table. The top row is just a restatement of our chemical equation. This is followed by the initial concentration row, the change in concentration row, and the equilibrium concentration row. We can begin by adding our initial concentrations from the problem. This is 0.750 molar N2O4 and 0.525 molar NO2. We can now build the change row, but again, we do not know from the problem in which direction the reaction will proceed. We must first calculate Qc and compare this to Kc. Qc is built the same way as Kc. In this case, we have the concentration of NO2 squared in the numerator and the concentration of N2O4 in the denominator. We can substitute our values in from our initial concentration row, and when we solve for this, we find that Qc is 0.368. Since Kc, which is 0.211, is now less than Qc, 0.368, the system will react in the reverse direction. This means that the NO2 concentration will decrease and the N2O4 concentration will increase. In this problem, the stoichiometric coefficients are 2 for NO2 and 1 for N2O4. Remember that these must be included with the overall extent of change, x. This means that for N2O4, we are going to increase by a value of plus x, and for NO2, we are going to decrease by a value of 2x. And so our signs are plus for N2O4 and negative for NO2. Finally, we can express the equilibrium concentrations. As before, we read down each column and perform the steps that are indicated. For N2O4, we begin with 0.750 molar, and we increase by x. The equilibrium concentration for N2O4 is therefore 0.750 plus x. For NO2, we begin with 0.525 molar and decrease by 2x, resulting in an equilibrium concentration of 0.525 minus 2x. Now for the algebra. First, we can substitute in our equilibrium row from our table. For our numerator, this gives us the quantity 0.525 minus 2x times the same quantity, 0.525 minus 2x. In the denominator, we have the value 0.750 plus x. The next step is to substitute in the value of Kc, 0.211, and multiply out the numerator. This results in the first term being 0.525 times 0.525. The second term is 0.525 times 2x with a negative sign. The third term is 0.525 times 2x with a negative sign. And lastly, we have 2x times 2x. Next, we clear the denominator and simplify. On the left-hand side of our equation, we now have 0.211 times the quantity 0.750 plus x. On the right-hand side, we simplify and our expression becomes 0.276 minus 2.10 times x plus 4x squared. We can now distribute on the left-hand side, giving us 0.158 plus 0.211x. Next, we can move everything from the left-hand side to the right-hand side. This now gives 0.276 minus 0.158 minus 2.10x minus 0.211x plus 4x. Then we can combine like terms on the right-hand side. This results in 0.118 minus 2.31x plus 4x squared. Finally, we can invert this and write it in standard form. Once again, we have to use the quadratic formula to solve our polynomial. Given ax squared plus bx plus c equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. From our quadratic, we see that a is equal to 4, b is equal to negative 2.31. Don't forget to write that subtraction as a negative sign. And c is equal to 0.118. We can now substitute these values into our quadratic formula. Once again, let me remind you not to type this straight into your calculator. It may seem like a shortcut, but you're much more likely to make mistakes. Work each step in the problem individually. First, we can square negative 2.31, which gives us a positive 5.34. Then we can multiply out 4 times 0.118, giving 1.89. Lastly, in the denominator, we have 2 times 4, or 8. The next step is to subtract under the square root sign. 5.34 minus 1.89 gives 3.45. At this point, we can take the square root and divide up our fraction into two terms. The square root of 3.45 gives 1.857. When we break up our fraction, do not forget to include the same denominator on both terms. We're now ready to divide. 2.31 divided by 8 gives 0.289. 1.857 divided by 8 gives 0.232. To determine our two roots, we now have to add or subtract as indicated. The first root is found from addition. 0.289 plus 0.232 gives 0.521. For the second root, we subtract. 0.289 minus 0.232 gives a value of 0.057. Notice that in this case we have two positive roots. We will discuss in a moment how we determine which is the appropriate route to use. We are now ready to calculate the equilibrium concentrations, but recall that we found two positive roots, either 0.521 molar or 0.057 molar. Up front, it appears that both of these could physically be concentrations. However, we have to look a little closer at the problem to determine which one is the root we want to ignore. If we take the larger of the two roots and substitute it into our equilibrium concentration for NO2, we find that we get 0.525 minus 2 times 0.521 molar. When we do this subtraction, we get a negative concentration, which is not physical. And for this reason, we see that the top root of 0.521 is too large, and we can ignore it. The correct root to use is 0.057. Now we can calculate the equilibrium concentrations. For N2O4, we started with 0.750 molar and increased by X, or 0.057 molar. This gives an equilibrium concentration of 0.807 molar. With NO2, we began with 0.525 molar and decreased by 2x, or 2 times 0.057. This results in an equilibrium concentration for NO2 of 0.411 molar. The last step is to check our answer. We substitute the values from the equilibrium concentration row into our Kc expression and calculate. When we do this, we get a value of 0.209. This is not exactly the Kc value we began with, but it is very close. The difference is likely due to rounding errors when solving the quadratic formula. Again, this value is close enough that we are confident in our answers. This concludes the set of lectures on calculating equilibrium concentrations from a known value of Kc. Please be sure to keep your list of steps at hand when working homework problems, as this will aid you as you work these. Also, make sure not to rush the algebra. It may seem tedious, but by working each step carefully, you will make fewer mistakes. Lastly, be sure to work as many problems from the book as you can. Practice is the only way to become proficient in working this type of problem.